So today I'm going to talk about the concept of debugging machine learning models with Python. So many of you might get into a specific field like generative modeling, supervised modeling, and miss on some of the basics and foundations of machine learning modeling that could help you to progress in the field and then be able to get deeper in a specific topic that you are interested in. So that was my intention when I wrote this book last year. So this is a book published last year by Pact. I wrote the book in around a year, and the topics are a matter of helping you to build the roots and the trunk of the tree of machine learning for you, and then be able to easily get deeper in a specific topic, or after a while, switch from one topic to another if necessary, which is the nature of industry, right? So think about these topics not as something you want to learn and become expert at all of them together, because that's not the intention, but you need to know all of them on a level and then get deeper in some of them, like generative modeling, like causal learning, and then see how you can benefit from them in different kind of problems you are interested in. So just an introduction about myself. I'm currently senior machine learning scientist at Recursion Pharmaceuticals. I'm based in Toronto. The company's headquarters is in the States, USA. I was director of machine learning at Cyclica Incorporation that got acquired by Recursion last year. I'm author of more than 30 scientific publications in machine learning and computational modeling, heavily in biology and chemistry in the field of drug discovery. I taught and mentored more than 2,000 trainees in machine learning, and that was the reason I decided to write this book, because in majority of the talks, webinars, and presentations I had, and also in my work, we get deep in one specific topic. But unfortunately, after a while, I see people are missing on some of the foundations. Also, currently, I'm top machine learning voice on LinkedIn. So let's first review some of the categorization we have for machine learning modeling. So when you think about machine learning nowadays, many people are interested in generative modeling or foundation models, right? So whenever you hear about foundation modeling, many of them are related to self-supervised learning. And supervised learning, which has been the main success stories across different industries, like for image classification, right? So when you want to think about your problem in a specific industry or in a specific topic, you need to first think about the problem without trying to translate that problem into machine learning problem, right? It's like you want to identify cracks in products in manufacturing pipeline. You want to predict risk of getting cancer in patients. You want to decide if you want to give loan to a specific customers in the banking system or not, right? You want to generate new images. You want to identify and learn new representations and features about data points. So when you think about them, then you can identify if there is a specific algorithm that helps you to tackle that problem. It's like, okay, now it seems that my problem is a machine learning problem under supervised learning. I have to look for developing a supervised learning model, or which is a matter of identifying decision boundaries or regression lines or hyperplane to be able to predict a continuous value or a label for unseen data points. So that's the main intention. Or you want to group data points together in the case of clustering, or you want to reduce dimensionality of the data in case of dimensionality reduction in general. So self-supervised learning has some similarity to both supervised learning and unsupervised learning, because sometimes we get new representation out of our data. So technically we can go for dimensionality reduction if you think about it in that way. But at the same time, we frame the problem to become a supervised learning problem without having data. So there are similarities between these different approaches. And I'm going to get into some of them during my talk, and you will have a generative machine learning, generative AI talk after this presentation to learn about that specific topic as well. But when you want to think about these problems, it's not mainly a matter of jumping and develop an interesting Python and PyTorch or TensorFlow based model to generate something interesting. At the end of the day, when you think about machine learning in industrial level, you have to think about different aspects of going from data into a machine learning model in production. So it's not only about one specific component of something we call machine learning lifecycle that I'm going to talk about next, but it is a matter of taking care of all components of that life cycle to be able to have a successful model in production. When you think about debugging, so that's an interesting term. So traditionally, I think it goes back to, I think 1930s, 40s, I don't remember exactly. And it is actually a matter of just having bug, for example, in a manufacturing pipeline. But in programming, when we think about debugging, it's mainly a matter of identifying issues in our code. It could be logical issues. It could be, for example, typo, doesn't matter, right? So that is established. So we have many tools and many approaches for efficient debugging. But when we think about machine learning, it's not about making sure our code works, but actually it is a matter of making sure we take care of data-centric debugging, model and prediction-centric debugging, and production-related issues that we have to make sure doesn't happen. For example, in data-centric debugging, we have many data biases and flaws in data that we need to pay attention to make sure the data we are using for modeling or how we are dealing with the data, unseen data in production is properly established, is in a way that our model can be successful in production. In model and prediction-centric debugging, we have many different topics from what you learn early on in machine learning, which is about underfitting and overfitting, to many different aspects of taking care of machine learning issues in production, right? So step by step, I'm going to talk about these topics, but this talk is not about getting deep into one of these. So you can get the book and get deep into each one of the topics I'm going to talk about today, or you can just stick to each one of them that you're interested in and find different resources and learn about them. There's a question, I think, in the chat. Okay, perfect. So when we think about machine learning modeling, something that you're most maybe interested in if you start in machine learning area is training and evaluation. So generating a new model, training a new model, validating them, and then get a good performance. Awesome. Or in generative modeling, seeing you're actually generating new data points that make sense. Great. But when you think about machine learning modeling and care about production state, then you have a machine learning lifecycle, right? We start from data collection. It could be external data sources, or it could be internal databases. And then we have to go for data selection to see which one of those data points would be appropriate for the intention and objective we have in mind. Explore the data, all the statistical analysis needed to make sure the data we are feeding into our machine learning model is properly selected. And for example, there are no outliers or any of those kind of issues in our model. Do the necessary wrangling, and if necessary, even do some pre-modeling, which means, for example, sometimes we might do representation learning. We apply some dimensionality reduction approaches to reduce the dimensionality of our data before feeding it into the main model, for example, could be supervised learning model, right? And then go for testing, deployment, and then monitor them in production. Okay, this life cycle is not easy to understand necessarily if you want to think about them all together, right? But if you consider these modules, these different components, it simplifies the process for you. Because then you know, First of all, you cannot become expert in each one of them easily. It takes time. Also, that's not the intention. So we have people expert in each one of these areas, right? Or just bunch of them together, right? But when you think about these modules, it would be easier to understand what's going on in each one of them, what needs to be taken care of, and how to communicate and work with your colleagues in academia or industry to make sure you have a successful model in production. So I'm going to start talking about machine learning performance because this is something that most people are interested in, although there are many things that come after that. Even if you have a high performance model and you took care of proper performance assessment, there are still things you need to do to make sure you have a successful model and reliable model in production. When you think about machine learning performance, the first thing that unfortunately get dismissed is what performance measure you need to use. As I mentioned, these are all from the book, but there's much more in the book you can learn from about each one of the topics I'm talking about today, but there are also some complementary topics you can learn about in the book. So the idea of selecting performance measure is to make sure that performance measure is not actually making your assessment problematic. What I mean by that, for example, accuracy is something that many people learn first. Traditionally, that has been the go-to in many different papers, but when you're getting into machine learning modeling, when you don't know enough about the data, you're not aware of the challenges in your data, accuracy is actually not a good performance measure to choose. There could be many issues like data imbalance that could cause problems in assessing performance of your models using accuracy. This is just an example. All of these box plots you see here are performances of random predictors. These are not good models. Just randomly, we are generating probabilities and labels. And I'm going to talk about the GitHub repository associated with the book, which is open source, and you can find the code to generate these. But as you can see here, accuracy goes just ups and downs just based on the distribution of the real data, right? But that might be fine in many other performance measures, like, for example, PRAUC, right? Precision Recall AUC, because Precision Recall AUC has a baseline for random predictor that depends on the true positive rate in your data. And we already know that, but that's not under control in accuracy necessarily. But we also have performance measures like ROC AUC and balance accuracy, as you can see in these boxes, that don't depend on the data distribution, the actual data distribution that you're trying to model, right? So that would be amazing, right? So you know the performances are not sensitive to those distributions. Why could that be an issue? For example, imagine you're using accuracy, right? The problem could be if you have a data set, a test data set, with 90% of them being blue data points. Imagine we have two categories of data points, blue and red, or 1 and 2. And now if you have a model that predicts everything to be blue, which could be simply an intercept in your model, right? So you're predicting everything to be blue, and all of a sudden, based on the accuracy, your performance becomes 0.9 because accuracy is defined as the total number of correct predictions over total number of data points. And because 90% of the data points are blue, you're predicting 90% of the data points correctly, so the accuracy becomes 0.9. So selecting the performance measure and making sure you're understanding the issues with each one of those performance measures is key in assessing performance of your models. Okay. So, but that's not enough, because at the end of the day, we want to improve performance of our model. Selecting proper performance measure just let us making sure there is no issue in that side. But at the end of the day, we need to go through processes like bias and variance diagnosis, model validation strategies. Many of you are familiar with cross-validation, different cross-validation techniques, error analysis, and different kind of tools in this toolbox that could help you to properly assess performance of your model, right? Reliably assess performance of your model and then plan for improving it. So the first step that get dismissed, unfortunately, is not to aim for improving performance, is to establish how to properly assess performance and then plan for improving them, right? So if you don't use proper performance measure, if you don't establish your validation strategy properly, then whatever you do in performance improvement might be biased, might have issues that you would not be aware of early on, and it hurts you later on when you try to push your model into production, or even when you want to release it as a paper or an open source model. There is something that seems to be minor but important, which is matter of visualization. Okay, so in visualization, the goal is to tell a specific story. You have a message, you already did everything quantitatively, and now you want to visualize to make sure your audience, your readers understand that message properly. There's a problem in visualization, unfortunately, in the industry, in many blog posts, and it's a matter of using misleading visualization. There are many things in visualization, making sure you're using a good plot, making sure you're having all the necessary quantitative measures, all of that is there. And then using proper colors, proper shapes, and everything. But if you take care of all of that, sometimes you could have misleading messages. And it is obvious in different blog posts when you're dealing with time series. This is just an example. So we have two time series here. One is blue and one is orange, which seems to be on top of each other when we are zooming out and seeing them in this large time period. But the problem here is there is a lag. So I simulated this data. And there is a lag between the orange curve, the orange time series, and the blue one. The orange, assume orange one is our predicted one, and blue one is the real data. So if, for example, you're trying to predict price of a specific stock, right? S&P 500, doesn't matter. So the problem here is, although it seems to be a great model, they seem to be overlapping with each other, just one day or one time period lag in the model, which exists to enforce that lag, to actually tell that story about misleading visualization, makes this orange one useless, right? Because like you want to predict stock price for the next day, but all of a sudden your model is just a one-day shift of actual data. So it would be useless. And it could be an issue in many different visualization techniques when you're using it for reporting on performance of your models, right? But imagine now you took care of performance assessment properly, and now you're ready for planning to improve performance of your model. There are many different techniques you need to be aware of to make sure you're not missing on opportunities for improving performance of your models, like in data cleaning and proper data selection, adding and removing features, right? Or even going through more complex representation learning, hyperparameter tuning, which many of you are already aware of, data augmentation using synthetic data in some topics, and using regularization, which usually is part of hyperparameter tuning, but many people prefer to consider that as a separate topic because it is usually very important, right? So these are techniques that help you to improve performance if you took care of performance assessment properly, and now you know what the performance of your model is, and then you're aiming to improve them, right? So this is just an example, which is not very straightforward. Imagine you have data with different quality and relevance to the problem you have at hand, right? This was something I worked on a couple of years ago, and it was a matter of seeing if we can benefit from data of different quality. Imagine this is the distribution of quality or relevance of the data, and not necessarily stick to the highest quality. Okay, that would be fantastic if we have enough data with highest quality, but the question is, could we benefit from other data points that we already have, right? From relevance perspective, if you think about it, that could fit into transfer learning, right? So we could benefit from images of cats, dogs, and many other uh, pets and animals, and then try to use that model as the baseline and then do transfer learning or fine tune it for a specific set of images or a specific problem, right? So that's about transfer learning. But there are other techniques like going step by step and apply filters and build models and go through this transfer learning process, or even build ensemble models on different parts of data distribution and assign a weight that tells us about quality or relevance of the data we used in the training process, and then make an ensemble of the predictions that we have for unseen data points, right? This is not something usual. So hyperparameter tuning or regularization is usually what you stick to when you're dealing with different kind of models, but sometimes you might deal with these situations that is not common. The question how we can deal with them. So this is another thing I try to provide for you in the book, but there are many other resources talking about different kind of challenges in dealing with complex data, big data, and also how you can improve your model, performance of your models in those situations. There seems to be a question in the chat box. Yeah, so the question is, would it be possible to address debugging in a distributed GPU environment? How can I lead my Python journey to be the best in cybersecurity? So I'm gonna talk about security and privacy next, but if you think about GPU, so there are different parts of hardware challenges, right? One is engineering, so how make sure you don't have idle GPUs, which is a matter of just benefiting from the infrastructure and hardware you have the most, right? The other part, which is the basic part, is just making sure actually your code works on GPU. That's the first step. So we have this engineering part, infrastructure part of GPU, and that we have that basic part. But there's something in the middle, right? So if you think about GPU, it is not supposed to change performance of your model drastically. It is the hardware you're using to train your model. But what happens is it can have a big effect on the power you would have, the possibility of training different models, right? If you can train in a specific GPU setting, if you can train 20 models within a week, or 20 models within a week, or 1,000 models within a week. So that's another part of debugging for the sake of GPU-based optimization, right? So the idea is how we can take care of computational efficiency and benefiting from GPU, like how we can make sure we have proper parallelization of the tasks, and then we can easily benefit from GPU. Because when you think about GPU, it's not only about the learning part, the optimization part of deep learning. You have a big code, big chunk of code for different aspects of data processing, and then getting into training your model and then testing them. And it is possible to benefit from GPUs to make sure you're benefiting to benefit from GPUs properly if you took care of those parallelization and those techniques in preparing your data processing and training and validation and inference, and make sure they are ready for GPU usage. So there's another topic which seems like mystery or irrelevant to machine learning folks, but that's not the case. That's about responsible AI. So for many people, it seems to be a more legal related topic or more business related topic. But there are many things that we can do as machine learning scientists and engineers to make sure our model is not against responsible AI, like to make sure we are taking care of fairness. The other topic which is very important under this is security and privacy, right? Of the data we are using. For example, if you're dealing with patient data or you're dealing with customer data, we want to make sure the data we are using is secure, and actually, if it is possible to regenerate part of that data, it wouldn't be infiltrated by attacks, right? So these are some of the topics that you need to be aware of. And as somebody who might not get into this field, you need to know some of the basics to make sure you are not building your models against these issues, although you might not want to become the expert in each one of these areas, right? And then we have transparency and accountable modeling and data model governance, which is another important topic. So, and usually, for example, if you're working in a company, this is something that a group is taking care of, but you're responsible to provide the information regarding the data you're using and how you're building your models for that team or that system that they set up to make sure the governance of your data and the models is taken care of properly. So this is one topic that is related to responsible modeling and the idea of interpretable modeling versus black box modeling. So for many years, banking systems use these interpretable models because they wanted to make sure those black box models don't come up with the predictions that are nonsense, and all of a sudden the banking system, people in the banking systems couldn't figure out what the issue is, right? So they prefer to stick to interpretable models, shallow decision trees, linear models for classification or regression, naive Bayes models, right? These two were the go-to in many banking systems, right? But we know in many areas nowadays, we are dealing with complex models, going from random forest and XGBoost and ensemble models to complex deep learning models, right? And the question is, how could we understand what is going on in our model to better take care of, for example, fairness, and also better identify opportunities to improve performance of our models, right? And that's something that fit under explainability, right? We have a very important and very interesting topic called machine learning explainability that provide us opportunity for improving performance of our model, for making sure we have a robust system, a robust model when we are pushing them into production, improving efficiency of data usage and benefiting from whatever infrastructure we have at hand. The reasoning could get better, and also we hopefully have a model that would be closer to the fairness notion, right? Nothing is 100% in machine learning, but we want to make sure actually we are closer and to take care of all those criteria, right? Sorry, there's another question, I think. If you have any question, okay, yeah, so I'm going to repeat that. If you have any question related with whatever I'm presenting, feel free to ask, either put it in the chat box, or I think you would be able to also start speaking, right? So ask your questions and I'll be happy to answer. There are specific algorithms and machine learning and Python libraries that help you in machine learning explainability. So whatever I provided in the book and you're actually learning about in this presentation, as I said, this is just the basis of different topics that you need to be aware of, not the depth of them that you can learn in the book or other resources that you can find out there. But for all of them, you have Python libraries. For example, for machine learning explainability, you have libraries like SHAP, you have algorithms like LIME, counterfactual, and you can benefit from them, or in the case of image processing, saliency maps, to make sure your features and your data are used properly, and even understand what is going on in the models, right? To understand what is going on in the feature space and the features that are used for predicting a specific outcome are actually informative for you in decision making regarding the next steps, either in modeling or in any other task that you have in your group. Okay, so whatever I'm presenting here, you most probably find Python libraries, and I talked about them in the book, and those will help you to establish these steps in your machine learning lifecycle. Okay, so performance, very interesting, very important. Responsible AI, very important. Unfortunately, just lately it became the attention of many people, but it is also very important. But something that is very important in machine learning modeling, specifically when we care about production, is engineering, right? So engineering is not something that only machine learning engineers need to care about. So machine learning engineers become expert in different topics in, for example, infrastructure or other things that would matter for engineering aspect of machine learning modeling. But as scientists, as even data scientists, you need to be aware of some of these topics to make sure you are not going against some of the best practices and some of the concepts that you need to care about when you're thinking about machine learning in industrial level, right? One of those, which actually became of interest in even open source modeling and academia, and it is one of the key components of modeling, is versioning and reproducibility. It seems simple, but it is very important, because at the end of the day, if you cannot reproduce whatever you develop, the inference and predictions coming out of your models, and you cannot regenerate the model that you had, you cannot take care of the machine learning lifecycle properly. You cannot go for a step-by-step model improvement, because if you cannot build the same model, train the same model using the same data, then how exactly you can benefit from new data points to make sure the model is getting better? If you cannot generate the same prediction, for example, in production for new data points, how you can be sure your model is reliable? This is just some simple examples. If you just change the random state for a split in the case of, for example, cross-validation, tenfold cross-validation, this is what you see can happen. So you have training loss and validation loss, and all of a sudden you have even different trends. It's not only about the changes in the value of loss at each maximum depth of an ensemble model. This is an example from the book, but the trend could also change, which is a big problem, because all of a sudden, by just not knowing what the split was in your cross-validation, you are having a different trend in training and loss change versus change of maximum depth in your ensemble model. This is a simple case. It could cause many issues in deep learning setting, in ensemble model setting, in simpler models, and all of that is related to making sure your model is reproducible and you're taking care of versioning. And it's not about code versioning only. Code versioning is something we care about in DevOps, right? We have Git, we have GitHub for cloud system, and then, or GitLab or Bitbucket or so. But in machine learning, you need to also care about data versioning and model versioning. You need to know what data was used to train a specific model or test a specific model. And then when you have a model, you have to make sure that model will be frozen, right? So you have a specific system to make sure that model generates the same prediction, infer the same output for a given data point. But that's not it in engineering. There are many different topics, and this is just some examples, some extra examples related to engineering. And as I said, you don't need to become expert in these, but you need to be aware of them and become expert in some of them that would be relevant to your roles and to your projects. For example, we have infrastructure testing, integration testing in machine learning pipelines, monitoring and validating live performance, which is very important to make sure the model is working as expected in production state, and also model assertion. So these are just some examples, as I mentioned. And for example, when we care about monitoring, it is important because we might deal with concepts like data and concept drifts, right? The issue is whenever you're building a model for publishing a paper. So you are working in development environment, and at the end of the day, you release a paper and that's it, right? But when you're working in a company, in healthcare system, drug discovery, Netflix, Amazon, banking system, doesn't matter, manufacturing companies, at the end of the day, you want to provide that model in production. And the idea is that model should work as expected, meaning work properly in the limit of performance that you saw in development environment. Not the same level, definitely those are unseen data points. You don't expect they work in the same level, but we want to make sure it is as close as possible. But sometimes we have issues like drift in our data, right? So this is an example. If you see the distribution of the features change when you compare it in the reference distribution, meaning, for example, if this is from development environment, the data you use to train your model, and this is the data you see in production. Just having a simple example, imagine you're training your model, for example, for Amazon. So that's not how it is happening. It's much more complicated, but just for having a simple example, imagine you're developing a recommender system to recommend clothes to individuals, or you're having a supervised model for a specific reason, but it is matter of clothing, right? And all of your data are coming from spring and summer, and all of a sudden you want to use that model for winter. And not only the season is changing, but because of change over time, maybe the fashion is changing, right? We have new styles. So the model wouldn't be necessarily generalizable, and it's not the issue of the algorithm or how you did the modeling, but you just have a drift in your data, right? Or there could be a concept drift associated with the model. So you need to be aware of these important challenges and topics. And deep learning, something that most people are excited about, and nowadays even generative modeling, which is a subcategory of deep learning, is a toolbox within machine learning. First of all, it is not parallel to machine learning, and most of you already know about that. But it is a toolbox to provide important and effective algorithms for specific data types you're dealing with, problems you're dealing with when you have enough data. So many people, when they think about deep learning, first thing comes to mind is, okay, we are dealing with big data, but that's not it. The specific series of algorithms that was built under deep learning, deep neural network modeling, it helps you to tackle problems for specific data modalities, and I'm going to talk about it. Just to review deep learning, when you're dealing with fully connected neural network like multi-layer perceptrons, then the idea is very simple, similar to ensemble modeling or logistic regression. So you have features, individual features. It could be age, gender, salary, or so, for example, in credit risk estimation or so. And then you put different layers. And the idea here is you're letting the model to automatically learn patterns, as opposed to some old school algorithms that they try to force a specific kernel and a specific function for those patterns. Here, we are letting the model to benefit from the data and identify those complex patterns. And this is just showcasing individual components of such networks, which are individual neurons. I'm not going to get into all the details. If you have questions related to that, I would be happy to go through more details, or maybe I can get into details of deep learning or different topics I presented in previous slides in another webinar. But what I want to emphasize is in deep learning setting, you can build models for different data modalities. And that's the question you need to have in mind first before getting into any sort of modeling. It's like, what is the data modality you're dealing with, and what are possible algorithms to use when you are developing a deep learning model? If you're already in the area, you already know about that. So I'm talking to people who are new in the area, right? So you want to use deep learning, and then the first question is, what is your data modality? Are you dealing with sequence data like text, like DNA? So you have sequence of information, and the question is, what are the possible algorithms to benefit from in this toolbox and build the model that would be successful, right? Or you're dealing with image shape data. So remember, it is not about text or images. It is about sequence data and image shape data and graphs, right? These are different data modalities. So text is one kind of sequence data. It is a very important one, but it's not the only one. For example, you can have DNA as another example. You can have representation of molecules as another example, right? For image shape data, it is very clear. We are dealing with these pixel-based 2D or 3D images. And the question is, what would be the algorithm to benefit from to build successful models for that data modality? Or for graphs, we have models to be successful for each one of these data modalities. Okay. And those would be convolutional neural networks, transformers, graph neural networks. And the question here is, so now that we know these are different algorithms, what's going on with generative modeling, reinforcement learning, self-supervised learning, supervised learning when we get into deep learning setting? So one challenge for people getting into deep learning setting is to realize these differences, right? To realize that when we are talking about transformers, you can use transformers for sequence data as one data modality and also images, but you can use it for generative modeling in reinforcement learning setting, in self-supervised learning setting, in supervised learning setting. So these are not parallel to these, right? So when we are dealing with generative modeling, because many people learning about these topics based on the hype, like nowadays, everything is based on LLMs or image generation like DALL-E, right? So when you think about it, then it's like, oh, when we think about generative modeling, it's about transformers. That's not the case, right? At the end of the day, each one of these modeling types has a specific objective, and you can benefit from different algorithms that are available to deal with different data types to achieve those objectives, to get closer to the goal under each one of these. Like if you want to generate new data, learn about the distribution, generate a new distribution, or do representation learning using self-supervised learning, or go for action-based and experience-based learning in reinforcement learning setting, rather than having all the data together and then go for supervised learning, right? So this distinction between type of modeling and data modality-based algorithms would be very important. There's something to be aware of. So if I go back here, I mentioned transformer is the go-to, for example, nowadays in large language models, in general, in NLP, most people are using transformers, but it doesn't mean that transformers is only useful for sequence data. We have transformers in the case of images, vision transformers, and some of the underlying mechanisms like attention in the case of graphs, like graph attention networks. So you need to be aware of the possibilities to be successful in a specific problem, right? Going back to what I mentioned at the beginning, so you need to first understand your problem from domain knowledge perspective, from business perspective, and then see what data is available, what is your data modality, and then identify opportunities in your machine learning and deep learning box to develop a model for that, and then taking care of different components of machine learning lifecycle. Okay, but in addition to these topics, there are a couple of topics that actually became attention of different people in the industry, because these are helpful in specific scenarios to make sure you're successful and you are having a reliable model depending on the objective you have in production state, right? So one of them is correlation versus causality. Majority of the model that we develop are correlation based. Deep learning model, many of them, machine learning model outside of deep learning setting, many of them are among those. And the problem is, so we might deal with spurious correlation, right? So nonsense correlation, like US crude oil imports from Norway correlates with drivers killed in collision with railroad trains. This is obvious nonsense. The problem in machine learning setting is it is not very easy to detect those nonsense relationships necessarily. So when we get into causality and causal learning, the idea is to aim for identifying causal relationships. I don't have time, unfortunately, to get into all the details of what's going on here. I have provided the basics of what's going on in causal learning in one of the chapters of the book, and there are great books already published by Pact and O'Reilly, and there are courses about causal learning. But you need to be aware of this does not necessarily come parallel to deep learning. Is like, okay, so when you have an image modeling, let's see if you can develop a causal model in that specific setting. That's not nowadays how it works. There are specific scenarios in which causal learning helps a lot, and there are specific scenarios, unfortunately, causal learning would not be efficient for. Another one is human in the loop modeling. Maybe you've heard of active learning, but human in the loop modeling is beyond active learning. It's about how you can benefit from expertise of people, your colleague, people you're working with in different components of machine learning lifecycle to make sure you're pushing a reliable model into production. Active learning is one example, which is a matter of not generating expensive data, for example, experimentally, but rather going step by step to make sure you have good data in each step that helps your model learns better representations, decision boundaries, and come up with better predictions at the end of the day, right? There are specific settings, there are specific scenarios in active learning setting, but you need to just consider human in the loop modeling in general to make sure you can benefit from expertise of individuals, because we are not yet, and maybe we will not be there very soon, to see just machines working together and human beings just watching TV and having drinks, right? So in each specific topic, like drug discovery, healthcare, banking system, we need to benefit from expertise of individuals to make sure we are pushing a reliable model in production and make sure that model is working as expected. Okay, so that was it. As I mentioned, the book has much more than what I presented in this talk. These were just some headlines of what you need to know and what is explained in the book. And at the end of the day, you need to care about this tree of machine learning. You need to build your foundation, which was my intention in this book. And then you go deeper in a specific topic you're interested in, either based on domain knowledge. Maybe you want to develop different kind of models for a specific problem like drug discovery, or you want to become expert in NLP or anything else, or in engineering side. But at the end of the day, having that a strong foundation help you to go to faster, go deeper in a specific area you're interested in, and if necessary, switch between different topics, which might be the nature of the industry you work in, right? So that was it, but I want to share my screen, share another screen, and go through the GitHub repo as well. So the book has an associated open source repo, so you don't need to buy the book to go through this repo. The repo is open source, but if you get the book, that would be helpful for you to provide all the context regarding what's going on in these notebooks. So this is open source. If you go to each one of them, there are associated Jupyter notebooks that you can benefit from. And Jupyter is, as you know, is the go-to when it's a matter of learning something new or teaching. That was the reason I stick to Jupyter Notebook. But going back to what I explained in engineering, when you're thinking about building pipelines and workflows, you cannot stick to Jupyter Notebooks necessarily. So think about these standalone Jupyter Notebooks as pieces of code to help you learn about some of these topics. So that was it for this presentation and the idea of debugging machine learning models with Python. All of the topics I presented have associated Python libraries I explained in the book, and also it is available in the open source GitHub repo you can benefit from. But the idea is not the book necessarily. The idea is to just know about these topics and start learning about them using any resource you are interested in, and make sure you are not missing some of the subdomains, some of the topics when you are getting deeper and deeper in a specific domain and in a specific kind of algorithm, because that would hurt you in long run. And it is not difficult to learn about these foundations before spending more time to get deeper in a specific area you're interested in.